Imagine hundreds of thousands of heavy steel entirely alone, surrounded by miles of deep, rolling water. This diagram puts that immense scale into perspective. If you stand one of these modern cargo ships on its end next to a skyscraper, the ship often wins. We're talking about structures weighing well over 200,000 tons. In everyday life, gravity is unforgiving. Drop a solid block of raw steel into a pool, and it plunges straight to the bottom. So how does a skyscraper-sized mass of that exact same metal stay comfortably above the surface? Naval architecture relies on the laws of fluid dynamics to balance the weight of the steel against the upward pressure of the water. To see exactly how this works, we have to look closely at the boundary where the metal hull actually meets the ocean. This diagram illustrates displacement. To float, objects must displace water equal to their weight. Red arrows represent gravity sinking solid steel. Stretching that metal into a hollow hull displaces drastically more water. Upward blue arrows push back, perfectly cancelling the forces at the waterline. Floating heavy metal depends on the massive volume of air trapped within the steel shell. In physical terms, the ship is an engineered air bubble, protected by a steel fortress, designed to manipulate water pressure to its advantage. Taking that theoretical concept and building it in the real world requires moving to a massive dry land construction facility. You can't build a 200,000-ton hull from the bottom up in one continuous piece. The sheer scale makes it physically impossible. Looking at this shipyard schematic, you can see the solution. The vessel is divided into massive, house-sized modules called megablocks, built independently in separate zones. Once complete, heavy transporters move these blocks into a central dry dock where they are stacked and welded together with millimeter precision. These specific welds carry an enormous responsibility. They must form an absolute flawless seal, protecting that critical internal air bubble from the crushing pressure of the deep ocean. Modern shipbuilding relies entirely on snapping together these gigantic puzzle pieces. Even a microscopic flaw in the seal could compromise the vessel's displacement and cause it to sink. Once that perfectly sealed hull enters the water, it faces a new problem: actually moving hundreds of thousands of tons of weight through an incredibly thick, dense fluid. Overcoming that sheer physical resistance requires a massive internal power plant. The engines inside these ships generate enough raw energy to comfortably run the electrical grid of a small city. This stern cutaway shows how that energy travels. The mechanical force channels down a heavy drive shaft, converting raw engine power into the rotational energy of the propeller, which violently pushes against the displaced water to generate thrust. Alongside those massive engines, the ship houses immense fuel stores, water filtration, and waste management systems, because out on the open water, there are no supply lines to fall back on. These massive vessels act as fully autonomous, self-propelled cities, engineered specifically to operate for weeks in complete isolation. And isolation is dangerous. Out here, a vessel is completely at the mercy of violent swells and towering storm waves. Outside the hull, the ocean is chaotic, unpredictable, and fiercely destructive.